Welcome to the Explainer. So let's talk about the ultimate mechanical parasite under the hood, your vehicle's alternator. Today we're diving deep into the hard math and the advanced diagnostics behind this hidden power debt. If you're a professional mechanic focusing on diagnostics, or maybe performance tuning and trade-offs, you are absolutely in the right place. Let's get into it.
All right, we need to lay down a foundational rule right out of the gate. Energy cannot be created from thin air. Every single watt of electricity comes directly at the cost of your engine's power reserve. Put simply, there is absolutely no such thing as free electricity when it comes to your engine.
To really put that into perspective, just think about the number 5.25. That is the exact mechanical horsepower your engine literally loses just to spin a high-output 200-amp alternator under full load. I mean, that's raw power stolen directly from the crankshaft. So here's our roadmap for today. We'll be breaking down the power debt, looking at internal inefficiencies, evaluating performance tuning trade-offs, advanced diagnostics, and, finally, smart alternator systems.
Starting off with Section 1, the power debt. Let's look at mechanics versus electricity. Let's think about the fundamental physics of how electrical demand actively steals torque. When you're calculating total electrical load, you're converting mechanical power, your torque and angular velocity, into electrical power. The kicker here is the efficiency factor. Standard units run at only 50 to 65% efficiency, so your engine essentially has to produce roughly double the mechanical wattage just to break even and compensate for that conversion loss.
Looking at standard conversion ratios, you can see exactly how electrical demand translates directly into lost mechanical horsepower at the wheels. For instance, if you're pulling an 80-amp load at 14.4 volts, you are drawing about 1,150 electrical watts. But because of those conversion losses we just talked about, your engine is actually supplying over 2 horsepower just to meet that demand. This right here is exactly why you have to properly size an alternator to match specific vehicle electrical demands without unnecessarily overloading the system. Moving on to Section 2, internal inefficiencies. Where is all that power actually going?
So looking inside the alternator housing, you can see exactly where that 35 to 50% of wasted engine power is bleeding off. Your copper winding resistance, the I²R losses, they eat up around 35% of your efficiency through sheer heat alone. Then the rotating magnetic field inducing eddy currents in the iron core, that steals another 20%. Add in the rectifier diode drops and mechanical friction, and you can clearly see how these internal losses specifically decrease an engine's net power output. It's basically a giant heat generator.
Now contrast your standard 50 to 65% efficient units against premium synchronous rectification designs, and you see exactly why upgrading internals is a game changer. By eliminating those standard diode drops with synchronous rectification, overall efficiency jumps up to around 80%. You are fundamentally keeping more horsepower right there at the crankshaft and drastically reducing internal heat.
Okay, Section 3, performance tuning and trade-offs. Let's talk real-world impact. Reducing total electrical load directly improves your 0 to 100 times. Seriously, under heavy load, your acceleration can actually increase by 0.1 to 0.4 seconds, mainly because the ECU is dumping extra fuel, up to 1.5 liters per 100 kilometers, just to compensate for that heavy accessory draw. This causes momentary torque loss and sluggish acceleration. Plus, all that mechanical resistance puts massive stress on pulley tensioners and creates intense heat. Always look for discolored housings during your inspections, by the way.
For competition vehicles, this is strictly a trade-off. In drag racing, doing a complete alternator delete and running on a lithium battery can save you 4 to 12 horsepower right at the wheels. Huge advantage. But say you're running time attack, you still need to maintain minimum charging needs at high RPMs. So instead, you'd select specific underdrive pulley ratios to slow the alternator by 15 to 30%. This minimizes the parasitic drag, freeing up 2 to 5 horsepower while still keeping your critical systems alive.
All right, Section 4, diagnosing conventional failure modes.
So, how do we catch a stressed alternator in the shop before catastrophic failure? Well, the classic symptoms are dead giveaways: rough idle or RPM hunting when the AC kicks on, or sudden belt squeal indicating tensioner stress or seized bearings. If the battery is draining despite the engine running, your routine inspection schedule needs to immediately target internal rotor slip ring or brush wear. And hey, if your voltage drops below 13.0 volts under load, you need to perform a voltage drop test to pinpoint whether you're dealing with a faulty voltage regulator or just poor grounding connections. When it comes to measuring the actual parasitic draw, an inductive clamp load test is your definitive workflow. You measure your base voltage, usually 13.8 to 14.8 volts, then turn on every single electrical accessory. Next, clamp that inductive meter right onto the alternator output wire. If the voltage falls below 13.5 volts at full load, you've got a definite electrical deficit and the unit just isn't keeping up with demand.
Another absolutely crucial check is the AC ripple test. Using your multimeter and AC voltage mode or an oscilloscope, you can instantly tell if internal diodes are failing and leaking destructive AC current into the whole system. Just check the battery terminals while it's running. Good diode health keeps it below 0.5 volts AC, but if you see an AC ripple above 1.0 volts, a failed diode is generating extreme internal heat and severely tanking your system efficiency.
And finally, Section 5. Navigating smart alternator systems.
Modern battery management systems have completely rewritten our diagnostic rules. Vehicles post-2010 rely heavily on sensor feedback loops and pulse-width modulated, or PWM, signals to dynamically alter the alternator's parasitic drag. It's all based on what the driver's right foot is doing. The ECU can completely drop the load during hard acceleration to free up power, and then maximize the field current during deceleration to recover that kinetic energy. This is where traditional testing will totally mislead you, because a perfectly healthy smart system might deliberately drop the voltage to 12.5 volts at idle just to save fuel. A simple multimeter test might make you think the voltage regulator has failed. You absolutely must use a scan tool with live data. You have to correlate that parasitic draw with specific RPM ranges to actually confirm if the pulse width modulation is functioning correctly. And this is especially critical if you perform major electrical component upgrades. You must use your scan tool to recalibrate the smart alternator settings. If you don't, the ECU will severely mismanage the new load. The vehicle's computer relies on monitoring the exact battery state of health. If you change the electrical demands without telling the ECU, you are asking for erratic idle corrections and messy fuel trim issues. So here's the big question to leave you with. Is your next electrical upgrade creating a mechanical power deficit your engine simply can't afford? Remember, electricity is never free. Everything comes at a mechanical cost. Understanding exactly how to measure, tune, and diagnose that hidden power debt is what separates competent mechanics from the truly great ones.